So I'm in my final year of mechanical engineering here at Laurentian, and today I'll be speaking to you about a vibration measurement project that was completed last year with DMC Mining Services and CROSH here at Laurentian. To give you an outline of the presentation for today, we will first start with the introduction of the Workplace Simulator Lab at Laurentian. We will then look at the CROSH-C grant used to fund this project with DMC, and then get right into the details of the project. And finally, we'll end off with the results and some acknowledgements. I'd like to start by telling everyone about CROSH's lab called the Workplace Simulator. In the lab, there are 3 pieces of equipment that can be used to simulate different workplace conditions, including an environmental chamber, Rotopod, and a metabolic cart. This lab can replicate vibration exposure using a Rotopod in a chamber controlling the environmental temperature and humidity as seen on the left. We also have a metabolic cart featured in this image on the right. The environmental chamber is able to simulate different temperatures and humidity levels that could be experienced by people, industrial products, and materials in the workplace. The system offers a temperature range of -15 to +40 degrees Celsius and can control humidity up to 100% at specified temperatures. The Rotopod is able to simulate movement and vibration along the X, Y, and Z axis. There are a couple of pre-existing attachments that can be mounted to the Rotopod table to be used in a variety of studies, or a custom testing apparatus can be built to be mounted using the T-slots on the table. This photo shows the Rotopod and the tabletop where different attachments can be mounted. As seen in the second photo, there's a suspension seat with armrests that can be attached to the Rotopod table to study the effect of different vibration profiles on the human body. In addition to this, an aluminum extruded structure can be mounted to the Rotopod to simulate a cab that an underground heavy equipment operator might sit in to further replicate the conditions that exist in the workplace. And finally, the Rotopod can be moved into the environmental chamber where participants may be exposed to both vibration profiles and different environmental conditions. In the case of this study done with DMC, a custom testing apparatus was designed and manufactured at the school, and only the Rotopod was used. At the lab, there's a metabolic cart where participants can be attached to while inside the environmental chamber. As you can see in the photos on the slide, this is someone who's attached to the metabolic cart while exercising in the environmental chamber, and on the right is a standalone photo of the metabolic cart. To fund this project, Dr. Katie Goggins and Dr. Brent Levers applied to the CROSH-C grant. This grant allows up to a $10,000 budget with funds to be spent within 12 months of the date of the signed contract. This grant also allows a postdoctoral fellow or senior PhD student to be the principal investigator involved and with the support of a faculty member involved with CROSH. It also allows for undergraduate and master's students to be involved in the research and receive funding. Access to specialized CROSH equipment is also granted when using this grant. And most importantly, applications for this grant that include an industry partner are favored over others, which helps foster partnerships with workplace partners or stakeholders. From this project, CROSH was able to develop an industry partnership with DMC. In underground mining, to connect 2 levels of a mine together without using explosives, a raise bore drill can be used to excavate a large circular hole. Raise bore drilling works by first drilling a small pilot hole from the first level to the second level, where the rods can be manually fed down the hole. These rods are then connected to a large reamer head with teeth that is pulled up through the rock to create the larger hole. As the drill moves up, the rods are lifted from the drill and set aside by operators. This repeated lifting done by operators puts them at risk from musculoskeletal injuries, such as lower back injuries. As seen in this photo of the operation of a raise bore drill, operators also sit close to the rock face during this process. This puts them at risk of injury from rock failures, noise, and dust. DMC Mining Services has developed an aftermarket product which can be added to automate some of the specific tasks carried out during drilling and allows the drill to be operated remotely. By adding this function, raise bore drilling becomes safer as it reduces the occupational hazards operators are exposed to at the rock face. However, due to the vibration from operation, the electronics of the system are being damaged, increasing the downtime of the drill. This study was designed and conducted to determine which vibration isolator was best at protecting the electronic components of the automated drill rod changing system. The electric component not seen here is the radio frequency identification reader, or RFID for short. This device works by using radio waves to transmit signals that activate an RFID tag, which can be used to track individual objects. The tag, once activated, then sends a wave back to the antenna, the RFID reader, where it is translated into data. The effectiveness of two passive isolators on the vibration reduction were tested using the Rotopod. The first isolator tested was the wire rope isolator, as seen in the picture on the left. The second isolator tested was a rubber one, which could be seen on the right. The isolators were switched out of the protective case as needed for the different experiments. Field vibration measurements were conducted underground at Valet North Mine in February of last year on an operating raised bore drill setup. Accelerometers were used to measure the triaxial vibration of the drill. In the photos here, you can see the underground drill setup. In the photo on the right, highlighted by the red circle, is where the operators would sit while the drill is running. In both photos, highlighted in the green box, is where the accelerometers were attached to the drill. The accelerometers were mounted in 3 different locations, one being a possible mounting spot for the RFID reader and its protective case. The accelerometers were fixed to the drill using duct tape. 2 samples were taken while the drill was in regular operation and stored in the accelerometer, which were later transferred to a computer for analysis. In the top photo on the slide, you can see an example of how one accelerometer was attached to the drill using duct tape. The bottom 2 photos give you the 3 different locations that the accelerometers were mounted. To simulate the vibrations experienced by the RFID reader, a custom testing apparatus had to be built. So the protective case and RFID reader were selected and supplied by DMC. To mount the RFID reader and the isolators in the protective case, 2 insert plates for the case were used. The RFID reader was attached to one plate labeled as the top plate, using screws and nuts. The isolators were then mounted in between the top plate and the second plate called the lower plate. This allowed for the RFID reader to be suspended by the isolators. The lower plate was then rigidly attached to the protective case. This assembly can be seen on the right, where the RFID reader, wire rope isolators, and the fixtures used are all attached. The protective case was then attached to a mounting plate. This mounting configuration, as seen in the top picture, was selected by DMC as it replicates the orientation of the RFID reader will be in when mounted to the drill. The mounting plate was added to the testing apparatus as it allowed for ease of assembly of the components inside the protective case. The mounting plate was then attached to the rigid box that was fixed to the Rotopod table. This testing apparatus was first designed in SolidWorks and a 3D modeling software, where I spent my time finalizing the design and assembling the components to ensure they would fit together. I then spent a week in the machine shop with Greg's assistants to build the rigid box and mounting plate. The following slide has a better photo of how the RFID reader assembly and its protective case fit inside the rigid box. As you can see here, you can better understand how the assembly came together and was mounted to the Rotopod table. The samples from the field data collection were then used to create a displacement signal that were then used to combine into a 130-second signal to be used to test the vibration isolators. To measure the vibration experienced by the RFID reader, 3 triaxial accelerometers were mounted in 3 different locations. As seen on this figure, one was mounted to the lower plate of the containment box, the top plate of the containment box, and directly on the Rotopod platform. On this slide are some of the photos that were taken during the testing in the workplace simulator lab. In the first photo in the upper left-hand corner, you can see how the protective case was mounted to the box using the mounting plate. In the second photo on the right, you can see the whole assembly with the wires for the accelerometer sticking out. And in the last photo on the bottom, you can see the isolator assembly inside the protective case with the RFID reader. Measuring the transmissibility is one method of understanding how vibration is transmitted through a structure. In the simplest form, transmissibility refers to the ratio between 2 points. In our example, we simultaneously measured the vibration on the platform and the vibration measured on a point on the RFID reader. The transmissibility, or decision of whether the isolator was working or not, is the ratio between the platform and RFID measurement. If the transmissibility is greater than 1, this means the vibration has been amplified and the isolator isn't working. And if the transmissibility is less than 1, the vibration has been attenuated and the isolator is working to some extent. Here are the transmissibility results of our experiment. The transmissibility results of the wire rope isolator are here in yellow, and the rubber isolator results are in this teal section. Focusing specifically on the transmissibility values, the green values indicate vibration was attenuated and there was some vibration reduction, and the red values here indicate that vibration was amplified. As indicated by these two highlighted green values, the wire rope isolator was more effective, reducing the input vibration by approximately 10% in the x-axis and 16% in the z-axis. From the field data collection, it was found that the main operating frequency of the drill was between 50 and 60 Hertz. The wire rope isolator that operates at 55 Hertz was chosen because it was better able to isolate the RFID reader from the operating frequency of the drill. We anticipated that the wire rope isolator would perform better in the testing due to this, and our results reflected that. The rubber isolator, on the other hand, amplified the input vibration at all locations and in all axes, with the peak in the z-axis at approximately 657%. From these results, the wire rope isolators can be used in the protective case for the RFID reader. These results will help decrease the vibration to the RFID reader, reducing or increasing the reliability of the automated drill rod changing system. This will reduce the operator's exposure to the occupational hazards at the rock face. DMC is now performing their own trials where the wire rope isolator is being used to mount the RFID reader. This project with DMC shows how CROSH's field to lab to field approach can be used to solve industry problems and create partnerships with industries in the community. It also demonstrates how the specialized equipment at CROSH, like the Workplace Simulator Lab, can be used to tackle relevant and important problems where the best solution is found. I'd like to take a moment to acknowledge everyone who made this project possible. Thank you, Jacob from DMC Mining Services for facilitating on-site data collection and providing all of the equipment necessary for the laboratory study. Thanks to Wes for doing the underground data collection and laboratory data collection during this pandemic. Thanks to Greg for helping me fabricate the testing apparatus. And thank yous to Doctors Katie Goggins and Brent Levers for your supervision and feedback at every point during this project. And finally, thank you to CROSH's Sea Grant program for providing my student funding while working on this project. I welcome any questions and just want to remind everyone about the HFE brainstorming session after this, and that if you have vibration-specific research problems in your workplace, please mention them there. Thank you.
Thank you very much, Elizabeth. We have some questions here in the Q&A. First, we have a common question, let's say. It says, Liz, great project, and I imagine a great learning experience. As a student about to graduate, has this project impacted the way you think about work or what you might want to do when you graduate?
It definitely has, I would say. I think it's definitely opened up a lot of areas that I didn't think about or didn't think I could go into. So I say like being involved as an undergraduate student has been very helpful.
Thank you. We have another question. It says, as an undergraduate student involved in a research project for the first time, what do you think are the most important things you've learned from the experience?
I think the most important things that I've learned is that I was able to directly apply what I learned in class to a real life problem, which puts it into perspective as a student that what you're learning in class even though it might not feel super important or exciting, not to get caught up in that, but to understand that there's potential to apply that knowledge in the workforce.
Thank you. Are there any disadvantages to using a bore drill as opposed to using explosive?
I am not too familiar with the difference between raised bore drilling and the use of explosives. Katie, do you have a better answer for that question?
Yeah, sure, I can help you with this one. So there are advantages and disadvantages to both. In this case, the raised bore drilling is very specific use to tunneling. There's only a couple situations where you can actually use it as opposed to explosives. Obviously, with explosives, there's more danger as far as the detonating and all of that. But for the vibration portion of it, there's drilling involved in both, and these findings are really, Liz, you can tell everyone these findings are really applicable to what type of drill and what type of situation.
Okay, thank you. I think the next question relates a lot with this one. It says, is this method more time consuming than using explosives?
I would say that it's dependent on the type of blasting that you're doing and the type of rock that you're trying to get through as well.
Thank you. Another question. Does the environmental chamber you mentioned in the beginning has any relation with vibration isolators?
If you were to set up a study using the environmental chamber and the Rotopod, you would be able to test the effect of different temperatures and possibly humidity levels on the types of isolators that you were studying.
Perfect, thank you. I think we have two more questions. Is there a plan to actually develop a design to use in the field, like a portable tool we can use to attach to a platform?
Sorry.
You want me to repeat that one?
Yeah, if you don't mind.
Yeah, sure. Is there a plan to actually develop a design to use in the field, like a portable tool we can use to attach to a platform?
As far as this study goes, this was specific to just testing the isolators with the RFID reader. Further development would be done probably on DMC's part if they decide to take it that way.
Thank you. We have another question. If a company approached CROSH about a research project, what are some details about the process will be important for them to keep in mind? I think this question is for CROSH staff. I'm not sure.
Okay,
Sure.
so I can take this one. Yeah. Liz, you know the answer though, but I can take it. Important details to keep in mind would just be, if you're going to come with a vibration specific project, then if you have an idea, and we do encourage you to bring it up in the next brainstorming session, if there's a problem as far as vibration goes, just any previous if there's any health problems, if you already had measurements taken here, any of those details, we also would need to know how invested you are in the project. And so, like Liz mentioned, this was a seed grant. And so to be able to do this kind of opportunity, we do need to have details in advance to be able to write it up, find whether there's been research done in this area, and be able to really help you solve that problem.
Thank you. Last question. The cost of making of this wasn't discussed anywhere. I mean, it's affordable or takes up a lot of cost?
I would say we were able to fund this project using the CROSH-C grant, where the funding was distributed between Wes and I, as well as the equipment that was purchased and using the workplace simulator lab. I would say that the CROSH.ca grant helps make this affordable.
Okay, thank you. And last question. Thank you everyone for your questions. Just a friendly reminder, try to type them in the Q&A section. Does the wire isolator have a longer life expectancy than the rubber isolator in an underground environment?
I would say yes, as the rubber isolator would be prone to possibly drying out or cracking or damage from other, different environmental things you would encounter underground.